Please welcome to my third presentation today, and I will continue with more about integrated simulation, how to integrate models and do large-scale simulation, and we'll also talk about different kinds of simulators and how we can reuse simulation models between those simulator types. So first the context, what is the simulator usage and what kind of simulators do we have? And when we reuse, we call that product line engineering or product family engineering. So we'll talk about that. The product itself is a product line. We have variants of the aircraft. But also when we simulate the set of models, is also a secondary product line, so to say. There's certain complications when we do that, so we'll talk about that also and some examples. So you remember this picture I showed you yesterday? We build the models early to do this development, testing and so on, but we reuse the models throughout the product life cycle, and it's very good when we can use mature models in the end. Through the customer can use them also. So we do simulation, we do training of the pilots with help of the models. And I will show later the flow of models. Actually, models have been like a business, so we buy models and we sell models also. So it's not only the main product, it's also the models. So this is an example of a very it's a simple simulator hardware-wise, but it's software-wise, it's the complete aircraft. So we can use it for initial testing and when we say training of pilots is one thing, but there's actually a value in training the engineers. Usually we compare it to automotive or to a collaboration with Scania. You know, Scania that makes trucks in Södertälje. Each engineer, they get a driver license for a truck in Södertälje. So the engineers, they are used to drive trucks, and they can learn and they can try the new features, so they get the feeling. In the fighter aircraft industry, we cannot do that. We cannot let every engineer try to fly the aircraft. So to use simulators in the early stage to educate and train the engineers is a very good feature that we obtain as well. So you get it. We talked about the holistic view and the elephant yesterday, but also to feel and try the product is another way to get this overall picture of the product and the system. So that's one kind of simulator. Another kind of simulator is full body simulator, where we have the actual cockpit, so the pilot can feel it. It's the same controls as in a real aircraft, and we have a dome, so you can see 360 images of the surrounding, so you get a whole other understanding of the flying and what you do. So that's another kind of simulator. And the third simpler way, this is a very old picture, but anyway, it tells that on the desktop, each engineer can have their own virtual aircraft on the desktop and do simulation of do the startup and see what happens if you do something, you have a mishap or something. So you can actually run the aircraft the way you want yourself. That is very cheap, of course. You don't need any hardware, it's just software-wise. But for all those kind of simulators, there are other kinds as well. But for all those kinds, we need a set of models. So there are the same set of models going into the core of the simulation of those different kind of simulators. So then we have the product line approach. We have the model set, all the models. I will come back to what kind of models we have here. But the set of models, we have a build process, And there we need the decision. We have to decide what kind of simulator, what is the purpose of the simulation, what kind of simulator is it. There can be other constraints, secrecy constraints, for example. All engineers are not allowed to see everything. So for some users, we have to just take a subset of the modules to integrate for a specific purpose. So all those decisions go into the process, and we take the version variants of the modules we have in the module storage, put them together, and implement in one kind of simulator. So this is the product line setting for the building simulators. And a typical simulator, the system simulator environment, our core is a global scheduler, but all the models are the solvers are locally. So it's not a solver, a global solver, it's local solvers. And the model update rate is between 1 and 100 hertz. is that time frame. Internally, it can be much higher rate for specific models, but on the global scale, it's around 1 to 100 hertz that they communicate. Just to get the feeling. And there are a lot of different kind of models. I talked about yesterday the physical kind of models. The fuel system, the hydraulic system, gearboxes, engines, landing gear, and so on. And then we had actuators and sensors, and the embedded software and the electronic hardware. There are different kinds of models. And as I said, most of the electronics and the sensors, if we say the sensors that the radar, for example, they're bought from sub-suppliers, so we don't develop them ourselves. But then we have the surroundings, like the runways, we have the atmosphere model and so on. And then we have, so to say, the framework, how the models should be connected, the architecture of the models that is included. We need to knowledge about that when you build the system. And then we develop, of course, in different kind of tools. So that's also, the more tools we have, the more tricky the integration is, of course. So classification of models. If you go from the left, we have those surroundings where we have the wind and atmosphere, ground roll, forces acting on the aircraft and so on. These are very stable, and these are not specific to the Gripen aircraft. So these are general. We can use them for other aircrafts, or actually some of them we could use for a car or whatever, because they are very general. For the specific aircraft, we have the system models, as I talked about, the engine, hydraulics and air control and so on. And then we have the sensors and actuators, that is the connection between the physical and the logical world. And as we see, for most of the models, these two are included in the same model. So we have the actual physical system and the actuators and the sensors included in the same model. So the interface of the model is logical, so to say. And for some models, there are pure ECUs that are not modeled in a very detailed fashion. It's more a logical model. And we have the connection to the core avionics, that is software intense. And then on the other side, we have the sensors and the communication system, that is the tactical system, the tactical parts, the mission parts of the fighter aircraft. So here is the things that is needed to be able to fly, and here's the things that is the value for the customer. I mean, for an air force, you need the radars and the communication system and so on. So we have tried to divide it into the flight critical and the mission critical parts. Because as we talked, I can show you. We talked about yesterday the layered approach where we had different life cycles for different parts. The hardware is a long life cycle. Infrastructure and operating system have a mid long time life cycle, and the applications are very short. It's the same with the models and the parts in the aircraft. The flight critical parts, they have a long life cycle. It's very robust. We need to test a lot. It should be very accurate. But on the mission critical side, we have the quicker loops. Here we apply more the agile approach for development, for example. So we talked about different development processes. It's the same here. We have very big difference in the process for developing flight critical things and for developing tactical things. And that's good, but it's also a challenge because we have more like different subcultures in the company. So sometimes it's not easy to get people used to those processes to work on the other side and vice versa. Is it understandable? Yeah.
Can you give some examples of the difficulties that happen because of this mismatch in cultures?
Yeah. For example, for flight critical systems, we have this standard RTCA 178, I think it is, that impose that we need to have oberoende. Not the same people that develop the things are allowed to test. Independent testing or independent verification. That gives more or less a kind of waterfall process here because we have it's handover. And then when we develop the process and we have templates for documentation and everything, it's applied for this process. And it's like as it is in a big company, we have the storage of templates, and the template department, they want to have a very pure and one template for everything. So it doesn't fit here. And the people coming from here, they are used to independence, so they are not used to working in an agile manner, for example, in the Scrum team and so on. So a lot of different things that is different and should be different. And of course, it should be not too different because then we cannot even speak to each other. So it's a balance.
What is HDD and HUD?
Head down display and head up display. So in this is a two-seater version of the aircraft have 3 head down displays in the front and 3 head down displays in the back. And there is 1 head up display. Head up display is where you see the things in front of you.
It's more like a dashboard. It's a dashboard.
Yeah, I think you saw it on this picture here. Okay. Here you can see the what the pilot sees in the head up.
So HMD is what, head middle display?
Yes.
Where's that one?
It's not on the picture, but you mean this one?
Yeah.
Helmet mounted display.
Oh, helmet.
So it is on the, we see it.
What kind of information are displayed? Like the tactical information?
Yeah, usually it is both. So it is the flight critical information, what height, what speed, how much fuel is left, but also the tactical information. That's also architecture-wise, it's a challenge to mix those because we mix things that coming from the safe side with things coming from that side, and what happens if these get mismatched in some way? It starts to overload your displays, for example. So we need architecture like RIC 653 architectures to divide the information from the source and just put it on the screen as late as possible. And here we can also see here in the core we have also divided the computers in flight computers and tactical computers. So I talked about different processes. It goes all the way into here. So here is actually the line where we split the processes from critical and non-critical, or flight critical and mission critical. Yeah. And also a recap from yesterday, I said that the system model is a representation of the system, and it's a good architecture if we have the same breakdown of the models as we have of the system itself. But that is tricky, it doesn't work always, and as I said here, we mix, in some models we mix the system itself, the fuel system for example, with the sensors and actuators for the system, so we don't really have the same breakdown as in the product itself, and that gives some implications. So typically we have the simulation models. They represent some product on some variant of the product, because we have those different product variants. And as I said, just we have a one-seater variant, a single-seater, and a dual-seater variant. So that's an aircraft with one pilot or an aircraft with two pilots. And that represents two different variants of the product. So product variant A can be the single-seater, and product variant B can be the dual-seater variant. And of course, when we set up the simulation models, we have to choose a slightly different subset of models. So the product consists of a set of subsystems, and for example, one is the fuel system, another is the engine. And the engine itself has different variants, so we can choose different variants of the engine. So on the simulator side, typically it looks like this. We have a set of subsystems, and they are included in the same simulation model. So 3 subsystems are represented in one simulation model, subsystem simulation model. In this example, the fuel system is represented purely in the fuel system model. Communication system, it has 2 variants, and this is also very typical. And sometimes we need to have variants of the simulation models due to testing or to training, because there are different requirements. If you cannot collect all the requirements and design a model that takes care of all the requirements, we need to have different variants. It could be, for example, the level of details. So for testing, we might have much more details in the model. For training purposes, it's important to be able to restart the model, or you impose some kind of fault, and then you will reset the fault very quickly to be able to train again. That is maybe not possible in the model, so then we need another variant for testing. And also some models are parametric, saying that, okay, here we had the engine itself and 3 variants, but engine model, there is an algorithm part that is common for all the variants, but we have a parameter set that we use to simulate these 3 variants of the engine. That means that the whole picture of the structure of the product, it looks not the same on the simulation side. And also we usually have a lot more here, because we have these variants of models. And that means that the variations are bigger on the simulation side. So the product line engineering, the variation and be able to create configuration, that challenge is much bigger on the simulation side than on the primary product side. And that is not all. We have talked to the aerospace, other aerospace businesses, and also automotive industries, and that is a common pattern that it looks like this. Yeah, so if we look at the model itself, when it flows through the development and the business, a lot of models we buy from sub-suppliers. They're typically equipment models and so on. And then we have a model development handbook that we would like them to follow. I will show you that later. It's easier for us to integrate when they also follow this framework, so to say. The models, we can integrate them with the pairwise or so on and do desktop simulation, typically in a tool like Simulink or pure code. And then we integrate more of them. So say that this could be the engine model. We connect that together with the FADEC, with a control of the engine, and then we can connect them, for example, to the fuel system to see the integration of the engine and the fuel system in some kind of laboratory. And then we integrate all the models. So we had all aircraft integrated, and then we get to the pictures in the beginning where we had the whole aircraft itself. And then take maybe all of them or a subset of those and integrate in a training simulator. And here we do training for teams, as I told you, engineering training. And then we sell the core and integrate it in a larger training facility, training simulator to the customers. So they actually buy models from sub-suppliers and we sell the models included in the training simulator to our customers. So there is a business in model business. So when it comes to develop models, we have this model development handbook. So the very important thing is to specify the need, the needs, the usage, the intended use of the model. Is it multi-purpose? Should it be included both in a training and a development simulator, for example? Or what kind of accuracy? What kind of how much details do we need? And then we have the specification, the verification and validation planning, the development of the model itself, design, verification, validation, and then we do export and have the interfaces according to our framework to be able to integrate in the simulator. And then something very important also is the status declaration. Because as we all of us that work with models know that the model is just an approximation. We talked also about that. It's not the truth, it's some kind of approximation or simplification. So we always had to declare what is the model capable of doing. Because the user of the model needs to know what is the boundaries of the model, for example. Is it verified up to 10,000 meters flying or just 3,000 meters, or what is the actual status of the model right now? And that also can change, of course. We can start off with a model that is declared to be not verified at all, but then it becomes more and more mature, and we can state that it works in a certain envelope, and an envelope can expand over time. So of course this looks waterfall, and I talked about we try to work agile, and we try to do that, but when it comes to actually do the documentation and so on, the model we need to have those process steps. And this handbook is freely available, so I have the link here, and I will send this out to you so you can download it if you want to. So we use this in research projects when we collaborate around model implementation and model development, but also in collaboration with sub-suppliers sometimes. sometimes they have their own process, so it's not easy to say that you should follow this strictly, but we have something to discuss around anyway. So when we come to the whole aircraft, we have a lot of challenges, of course, when we should integrate all those things. So the simulators themselves, they evolve, and we have different operating systems and simulated platforms. I mean, we go, for example, from Unix to Linux, from big engine to little engine, or if it is vice versa, I don't remember. But this kind of problem, this kind of evolution is one problem, that so to say should be platform independent as large as possible. There are many models, and some of those are legacy code, Fortran code from the 70s or even 60s maybe. We have variants of the system, as I talked about. We have a variant of the engine. We have many variants of the engine that has to be represented in the models. But also we have variants of the same model, meaning that we can have different fidelity, levels of the model. And also, of course, we have versions of models. We find errors, so we have to update them. So as any software, it comes updates all once in a while. That's also important in the status declaration to understand, is that this error in the old version, is that affecting my simulation right now? If that new version is not declared properly or verified, it's maybe better to choose the old one, because the error doesn't affect what I should do right now. And also, as I told you, we have parametric models with different sets of system parameters. So there are some challenges making the whole set of models very large. So to pick the right version and variant of each model is a task itself. So then we introduced this configurator thinking, the concept of configurator. The same as when you buy a car or a laptop or whatever, you go into a website and you click and see, I choose this option, I cannot choose that because there's a mismatch and so on. So I tried to do that. We're in a research project called Revamp right now, together with Chalmers and Karlstad and KTH, where we look on tools to do this. But typically, go back to this picture again. We have these assets in the model storage with variants. And here we should point out, it's not only the models themselves, it's the specification of the models and the status declaration of the models connected to the models. So it's not only the software, so to say. And the model variants and the metadata had to be described so we can choose, and we have the description what is matching and what is not matching. And the models, some of the models are also configurable, meaning that there are some kind of switches. For example, flight control model today is it's one model, but it fits both in the single-seater aircraft and the dual-seater aircraft. So it's just a runtime parameter switch, so we can choose very late, or it's included when the user is building, but it says I want a single-seater aircraft, and it automatically sets the parameters in the right context. So then we come to the notion of binding time. Are you familiar with binding time? No? So we'll go into that. During the build and integration, configuration, build and integration of the set of models, we have different binding time alternatives. So for example, we can, in the first step, when we take the models, we can check out a subset of the models. So there we choose just a subset. So that's the early binding time. Then when we compile, we can have compiler settings that is configuring some of the models in some sense. For example, it should be run on a Unix platform or on a Linux platform. So that's compile time binding. And then during execution we can have these runtime parameters. So we can have the single seater or the dual seater, for example, that is set during execution. So that is called runtime binding. So binding time is important here, and it should be known up here. So in the process, when you choose, you should know from the start where is the binding time for different alternatives, different variations in the build. So typically we have post-processing here for in the compiler. If defs in the C code, for example.
Is it time it takes to execute, or could you please be elaborate much more? Is it a time to execute, or?
No, I'm maybe went too fast here. Binding time means what time, at what point in the time during the integration of models do you do the choice to choose whether it should be one version or another version of the model. So, I mean, we do that many times. So each time we build a simulator, we go through this process, and then some models we do the variation in checkout time. For some models we do the variation in compile time, and for some other stuff we do it in runtime.
Okay.
And there are different pros and cons with doing that. So the aspects of binding time, so in checkout time, that creates different source code variants. We get the subset of the different source code variants. In compile time, we get different object code variants, and in runtime we get different instances. It has different properties. So typically, checkout time binding is used for the reliable configuration. I mean, if we have chosen one version of a simulator model, we cannot accidentally use the other one during simulation. Compile time is used for implementation-oriented configuration, like different platforms, for example. And runtime configuration or binding is used for fast reconfiguration, because then we can reconfigure in the simulator itself. We can switch between the one-seater and two-seater. So we don't have to go through the process again. An example of checkout time binding is when we have security or IP aspects. For example, the hydraulic engineer is not allowed to see the radar system model, for example. So then he can pick a simplified, not secret variant of the radar model. So that is checkout time used for.
What's IRP?
Intellectual
Rights.
Intellectual
rights.
All rights.
IP.
yeah.
IP.
Secrecy. So to say, yeah. Yeah, and as I said, example is platform, and example runtime is reconfiguration. For example, at the training site or in the development simulator. So, summary. Reuse is really good when we can create things early, front loading, and use models to understand the problems and discover defects early. But when we can reuse the models throughout the process and also sell them, integrate them and sell them to our customers. We have the maturity of the product out on the customer site is higher, is my belief in a way, than if we have the non-model based way of working, the traditional document based way of working. And I come back to this picture because I like it and I have made it myself. Once again, when we can use the models for collaborating, understanding each other, communicate, and we can use the same models for doing transformations, simulations, transformation to code or whatever, and do desktop simulation to be able to understand and get a good understanding and a deep knowledge about the system, to be able to propose modifications, for example, and discuss them together with our colleagues and use the languages that we all understand and do the mathematical oriented languages and simulation. Then we have a really good model-based systems engineering for cyber physical systems. So that concludes my presentation. Thank you.
Any questions?
I just have one question.
Hmm?
In the parametric variant you mentioned,
Yeah.
is it related to the calibration of the engine?
Yeah, it could be that, but it could also be if you have variants and they, for example, have different size of the inlet, for example, that could be a parameter that is just set in the simulation model. Could be a lot of different things.
So you have a basic version, and so you create variants based on the different engine options, for example.
Yeah. So it's called data-driven design. We have the algorithm is stable, and we have data, so we parameterize data-driven design, and that is more. It could be complex to create it, but when we have it, it's more flexible and more. Don't have to retest everything all the time. So it is.
So to find out the parameters, you also do kind of testing and calibrate the parameters, or again the parameters also obtained based on the simulation.
Yeah. Usually, during design we have some CAD model or whatever, so we can calculate and try to find out the right parameters.
Okay.
But then when we validate the models against the real world, then we calibrate and adjust it, so we get as good as possible. But of course there are uncertainties and so on everywhere. So, and we would like to use the kind of methods we have learned earlier to actually work with, understand how good the models are also. But that's the next chapter, I think. Yeah.
Other questions?
Yeah.
I learned from slides that while doing communication system simulations, there are two operations: testing and training. Could you give more details about training? What are you doing while training?
Training, for example, for a communication system could be that the pilot is training to fly in the training simulator, and then he should communicate together with another pilot in another aircraft. So they have to set the right channels on the radio and doing all the. I'm not into I'm not the pilot myself, but I know there are a lot of steps to do to be able to communicate and maybe to send the information, pictures or whatever to the other guy. So on the training facilities there are several training simulators. So they train together and they see how to communicate between the pilots during an operation, a mission.
So what's the difference between training and the test?
Yeah, testing is more that we test that the development is okay for this communication system. that the software is working as it should, and the hardware and the software together is working as it should, and so on. So that's more that we verify that the system is correct. But training is that the pilots are able to train the system when it's ready. So training is usually in a later stage than the development testing.
And the training is not only for the pilots.
No, that's right.
So also for the engineers that they are going to develop
Yeah,
this kind of software.
that's right. That's right.
So and also you mentioned that the mission critical software is usually developed in agile way, which is has a short life cycle.
Yes.
Yes, and I know there are a lot of web applications and websites that also developed in this form, in this fashion. So I think there should be some difference because even it is mission critical, not less critical, than some flight, some core software, but they are also critical. And I think there is some standard that you should set certificates your software, and then you can use them. You can apply them into usage in the aircraft. So this kind of agile, do you think it is really similar to what they use in industry, which they don't ask for such kind of safety?
I absolutely agree, and I mean, it's not agile if you go to Spotify, for example, and see how they work with agile. We have a lot of hardware. We rely on the hardware, so the hardware-software integration is a much larger task than in Spotify application, for example. So we have to adopt the agile framework to our processes and our product. So it's not really the same.
Yes, so I think the verification, the verification steps is also very important.
Yeah, but the verification step is more important on the flight critical side than on the mission critical side, of course. But there are, of course, a lot of verification to be done also there. But we don't have the requirement on independent testing, for example. So the same engineer that developed the application can also be included in the test team, in the test activities. Yeah.
Since we have different platforms of modules, is it possible to have one model for all the system? For example, aircraft, we do have software, hardware, and do we have unified model for all the aircraft?
Yeah, I think it should be possible, but as we have different cultures within mechanical engineering and software engineering and so on, it seems that it's very difficult to get engineers to adapt to one single tool or one single to input to one single model, because there are some differences in how to specify and simulate things depending on it's a mechanical or software part. But if we don't get down to details in a very not detailed fashion, there might be possible to have one large model for everything in one tool.
Because that helps interaction between equipment.
Yes.
For example, if you have an aircraft, you have the landing gear working properly, and the button that we are using is short.
Yeah, yes, that's true. And we have actually also a research project looking into how to be able to have, in this case, is a Rhapsody tool that we use to create a large model, but not so detailed. So the T-shape, it's not so deep, so to say. Yeah.
Any other questions? All right. Thank you very much, Henric.
Thank you.
And just a small gift from us.
Thank you very much.
Thank you. Thank you very much.
Thank you all for listening and for your questions. Thank you.